Okay. So we started our discussions on symmetric matrices in the last class, and we saw two things in the last class. Number one is all eigenvalues of the symmetric matrices are real, and the eigenvectors can be chosen as orthogonal. If they can be chosen orthogonal, they can be chosen orthonormal as well. That's not a big deal. So there are two big things we saw. If we have these things, if we can control these things, lot many things can be subsequently controlled. Yeah. But then this controlling these things is also a big deal. Yeah. One need to understand lot many things. Okay. Okay. So today's topic is positive definite matrices. So how do I know that a matrix is positive definite? How do I know? And this is, of course, symmetric matrices. We are talking about symmetric matrices. These are all related to symmetric matrix, okay? Positive definite symmetric matrices. And these matrices are again real. Real. We have been working on these matrices, and that is what we say S and S transpose are equal. And we have seen that all their eigenvalues are real, and the eigenvectors can be chosen to be orthogonal or orthonormal. So how do I know that a matrix is positive definite? So the very first test that you can do is all lambdas are positive. If all lambdas are positive, lambda means the eigenvalues. If all eigenvalues are positive, we conclude that it's a positive definite matrix. Now, how far you can go, whether all the eigenvalues are positive or not? Well, if it's a small matrix, a 2 cross 2, 3 cross 3, that's okay. You can check it. But if it is, say, 100 cross 100, that would be difficult to check, isn't it? That you cannot check. So there are a couple of more tests. Sorry, that actually concludes that uh, the matrix, the supplied matrix, is a positive definite matrix. Okay. So what are those tests? Test number 2. What is leading determinant? Leading determinant means if you have a matrix like this, so you have the elements So the leading determinant is the determinant made out of this, the determinant made out of this. Just a second. Sorry for the interruption. Yeah, the determinant made out of this element, the determinant made out of, let me erase it a little bit so that it will be easier. Okay, the leading determinant. So the leading determinant would be this one, this one, okay, and this one. This system is hanging, this Microsoft whiteboard. Okay, so this is what the leading determinant is. We are finding determinant along the diagonal, starting from 1, 1, 2, 2, 3, 3, 4, 4 for all the sub matrices. Yeah, that would be a good word. Determinant of all the sub matrices. Must be greater than 0. Okay. What is test number 3? So all pivot element are greater than 0. That is, during the elimination process, whatever pivot elements that you get, that would be, of course, along the diagonals, that has to be positive. Test number 4. The matrix S can be written as A transpose A, where A is a matrix with independent columns. Test number 5. For all vectors x not equal to 0, the energy x transpose S x is greater than 0. So these are the 5 tests. You perform any one of the tests. If it is true, then the matrix is positive definite. You need not perform all the tests. If any one of the tests is okay, it is true. Okay. So we'll start with uh, the last one. We'll start with the last one, the energy definition. Okay. Because this last one, actually, if you understand, the rest of the things becomes easier. All the lambdas are positive. I did not elaborate on that. That's quite obvious things. Yeah. Test number 5. Okay. In order to go for test number 5, So I'll start with 5 first. Let S is equal to I. We start with the identity matrix, okay, and check whether it is positive definite or not. So if S is equal to I, what we have? Do we have what are the values of lambdas? All lambdas I equal to 1 to n, they are all equal to 1. So it's according to test number 1, this matrix is positive definite. And it's positive definite. But then we are here to test the fifth one actually. So what is X transpose I X? Can I write it X transpose X? Now, if X is not equal to 0, what is X transpose X? This is of course a, a square. It is a square, right? It's a square. So the same elements are being multiplied and added. So it's nothing but a square. So hence X transpose X is positive, right? Now we'll go for something else. Let us go for a 2 cross 2 matrix. Let us say X transpose S X. And I'm writing this one as X1, X2, let us say 2. The matrix that we want to talk about is 2, 2, 2, 2, 1. X1, X2. Now, is this S matrix is positive definite? This is not actually, because the determinant is less than 0. So what I'll do is I'll simply make this one 3. Yeah. So how much is this? How much is this? X1, X2. 2x1 plus 2x2, 2x1 plus 3x2. So how much this is? You have 2x1 square plus 2x1 x2 plus 2x1 x2 plus 3x2 square, which is equal to 2x1 square plus 4x1 x2 plus 3x2 square. Now, can you say that this quantity, this polynomial, would ever be negative? Is it possible? There are different ways I can show whether this is positive or negative, but just think about it. In any way, can you say that this polynomial would ever be positive, would ever be negative? What if I write this one as uh, x1 plus x2 square. So this becomes x1 square plus x2 square plus 2 times x1 x2. So yeah, I have here 2x1 square. So let me multiply it with 2 so that I will get 2x1 square plus 2x2 square plus 4x1 x2. So what is remaining is x2 square. Now the same thing I have written in another way, x transpose s x. Now look at this. Can you say that this quantity will ever be negative? Never. This can never be negative. Well, not that it's not possible that all the equations we can derive in that way. There will be some situations where things would go, say for example, we have this is x, this is y, this is uh, x transpose sx. Okay, so based on this, based on this equation, based on this equation, we can always say that this first term is positive, second term is positive, but the middle term If both the numbers are positive, then middle term is positive. If both the numbers are negative, middle term is negative. If if one is positive, one is negative, then the middle term becomes negative. But the question is, uh, will it ever go beyond this area? Will it ever go beyond this area? That is on the negative side of x, y. Or so to say, is it ever possible that the middle term will overwhelm, or the middle term would be, whenever the middle term is negative, its absolute value is larger than the sum of these two absolute values. That is that is what I'm writing. Is it possible that 4 x1 x2 absolute value is greater than 2x1 square plus 3x2 square whenever either of x1 or x2 is less than 0? Is it possible? So if this is possible, then this matrix S, the energy of this matrix S will be negative, and this won't be positive definite. But then here is one solution that we saw. Here is one way that we found out. Well, this clearly says that this x transpose Sx will never be negative. Okay. But then, having said all this, what is the relationship between this x transpose Sx with lambda? What? A, it's not how, it's not what actually. How? Mm, how x transpose Sx? Oh, how S transpose, sorry, how x transpose Sx is related with lambda greater than 0. Oh, it is related. Let us see that. That is actually important to us. Okay, if Sx is equal to lambda x, that's what the way we find eigenvalues, right? Sx equal to lambda x. Now let me pre-multiply with x transpose. X transpose S x equal to x transpose lambda x, or I can write this one as x transpose S x equal to lambda is a scalar quantity, so x transpose x. So x transpose x is again a positive number. Lambda is greater than 0. So obviously x transpose S x is also greater than 0. This is positive. This is greater than 0. This one is also greater than 0. So that's it. X transpose S x is greater than 0. But then there is one more thing here. What is x transpose Sx? Can I write in this way? If I consider x to be one of the eigenvector, then everything looks very fine. Then x is a vector. I can write this x as a linear combination of all its components. So let me say x is um, x is what x? X is c1 x1 plus c2 x2 plus cn xn. That is my x. Mm, okay, this multiplied by s. What is the transpose? c1 x1 transpose plus c2 x2 transpose plus Cn Xn transpose. This I can write it as Sx is nothing but lambda x. So can I write it in this way? C1 X1 transpose plus C2 X2 transpose plus Cn Xn transpose multiplied by this. I can write it as lambda x. So I have C1 lambda 1 x1 plus C2 lambda 2 x2 Cn lambda n xn. Okay, so how much is that? Rho, I mean this vector transpose multiplied by this vector. Can I write this one as, again it's the same, mm, C1 square lambda 1 x1 transpose x1 Cn square lambda n xn transpose xn. I am omitting all mm, those multiplications like x2 transpose x1. Everything are omitted. Why? Because the orthogonality property. So xi transpose xj becomes 0 because of this. And this value c1 square, c square, positive quantity, lambda is a positive quantity, x1 transpose x1, xi transpose xi, it's again a positive quantity. So this is always greater than 0. Yeah, so that's it. Now you tell me what happens if uh, what's the What about the positive definiteness property of S1 plus S2 if S1 and S2 are positive definite? What about the positive definite property of S1 plus S2 if S1 and S2 are symmetric positive definite? What happens? We use this property. Yeah, X transpose SX. So X is any vector. So I'll write X transpose X. So this has to be greater than 0, isn't it? So how do I prove that? Whether this is greater than 0 or not? Simply multiply this. So this becomes X transpose S1X plus X transpose S2X, which is greater than 0. Because individually both the components are greater than 0. So that's greater than 0. Okay. Okay. We'll stop here and we'll see in the next class few more things. Okay. But then one good thing is that today I see more involvement in the Microsoft Whiteboard. I guess lot many students have started installing that. Thanks to the students who brought it to my notice, and thanks to the guy Deshpande.